Hello, my name is Anna Schartman. I'm a PhD candidate in the Ocean Sciences Department at the University of California, Santa Cruz. I'm an organic geochemist and paleoclimatologist. So this means I use chemical fossils preserved in sediments and rocks to understand past climates and ecosystems. Essentially, my research at UCSC focuses on the history of open ecosystems over geologic time. So open ecosystems are any with a discontinuous canopy and a grass-rich understory. In Africa, where my research is focused, savannas and grasslands are critical resources that cover about 50% of the continent. The grasses in these African subtropical ecosystems use what is called the C4 photosynthetic pathway. That's a carbon concentrating mechanism that evolved to help these grasses compete under low CO2, high temperatures, and in dry and seasonal rainfall regimes. Conversely, the trees and shrubs in these African savannas use the more ancient and standard C3 photosynthetic pathway. Importantly, most of these open ecosystems are very young in the span of geologic time. We think they date largely to the Miocene epoch. That's a period of Earth's history that stretched from about 5 to 23 million years ago. And this was an epoch we think that experienced warmer climates and higher CO2. My research focuses on the region of Northwest Africa. I used chemical fossils of ancient plants preserved in marine sediments to answer the question, when and how did grasslands and savannas first arise in this region of the world? For this work, I produced a record of plant biomarker carbon isotopes and abundances through the Miocene. So age is shown here on the x-axis. The carbon isotopic composition in the top plot tells us about the photosystem that plants used. More positive values indicate more C4 grasses. Plant wax abundances in the bottom plot tell us about plant growth form. Grasses produce more of the biomarker called C33N-alkane than C29N-alkane compared to woody vegetation like trees and shrubs. So in this plot, higher values indicate more grasses. In essence, these plots show that in the early Miocene, so older than 15 million years ago, forests and woodlands composed of C3 trees and shrubs likely dominated. At 15 million years ago, a grass-rich savanna developed and expanded, but importantly, it was composed of C3, not C4 grasses. So this represents a non-analog ecosystem that does not exist anywhere in the tropics or subtropics today. Finally, the C4 grass-rich savanna replaced the C3 savanna in the Miocene starting at about 10 million years ago and has been the dominant ecosystem on the landscape up until the present. So this ecosystem history shows that the original landscape opening in the Middle Miocene and subsequent transformation into the C4 savanna in the Late Miocene occurred during periods of global cooling and aridification. Future climate change is projected to equal or even exceed these Miocene changes in magnitude, for example, in atmospheric CO2 concentrations and global mean surface temperatures. So the geologic record here indicates that a dramatic reshaping of subtropical savannas could occur in the future. Of course, with the outcome dependent on the nature and strength of the feedbacks that operated on these ecosystems, including those of human systems. Thanks so much for listening, and thanks to the ARCS Foundation for the generous support that supported this research.